Today we're going to be talking about graphing radical functions. And so y equals the square root of x. Let's talk about some values that we can be plugging in for x. Now make sure your values make sense. Make sure all your values for x are perfect squares so that when you get an output for y, it's a whole number. So 0 is the first perfect square. That gets you an output of 0. 1 is the next perfect square, so that's 1. And this is key to remember. If I go up 1 over 1, it's not the slope because it's not a line, but that's going to help us with our vertical stretch or compression. If you plug in 4, which is the next perfect square, you get 2 as an output. So that's a good point. And then the last one that we can really fit on our grid is 9, and that is 3. So this is what our graph looks like. And I like to call that the one-wing bird. And I'll explain why in class, because it's, Marnell humor. So domain. You can't square root any negative numbers, and we're only graphing in the real plane. So x has to be greater than or equal to 0, because I started at 0 and went to all the positives. Now the range, when I square root, I only get positives out, so I started at 0 and went up to 1. So y is greater than or equal, or I went from 0 up, so y is greater than or equal to 0. It doesn't stop at 1, it goes up. But notice how as x gets bigger, y is getting bigger, a little bit smaller. Okay, our radical functions, all the shifting of this, and it's nothing less than what we've been doing. If it's under the radical, and you're shifting left or right, it's h. Your vertical translation, that's up and down, and that's going to be the number that's being added outside. Vertical stretch or compression, remember, this means y's are being stretched. Now, if it's less than 0, you reflect across the x-axis. Now, inside, remember to factor it out. We're going to do an example, but make sure that guy's factored out. That's going to be a horizontal stretch or compression, and that's if that b is less than 0 or negative, it's going to be a reflection across the x-axis. Okay, describe the transformations, graph, give the domain and range. Let's give the domain and range after we graph. I think it makes more sense. So this +1 under the radical, that means left 1, it's opposite of what it looks like since it's next to the x's. The +1, that means up 1. And then the 2, it's outside the function, outside your parent function, which is the square root. That is going to be a vertical stretch by 2. Now, on the first slide, I graphed the parent function, y equals root x, and I'm going to put that in dashed. You don't have to put that in if you don't want to. I just want to show you guys what it looks like when it's stretched. So that's your parent function. Now, basically, I'm going to take this function, and I always start with this point 0, 0. I shift it left 1, up 1. Now, the vertical stretch of 2, make sure you get me a value in there. That's taking this point, shifting it, but also stretching it up by a factor of 2. So it was at 1, now it's going to be at 2. So I went up 1 over 1. I'm going to go up 2 over 1. To get to this point, I went up 2, but over to the right 4. I'm going to go up 4, because it's a vertical stretch of 2, into the right 4, because I'm not stretching the x's at all. So that's what that graph looks like. Now, domain and range. Domain, what's the smallest x value? x value, smallest x value is -1, and it goes to the right. So therefore, x is going to be greater than or equal to -1. The range, it starts at 1 and goes up. So your range is y is greater than or equal to 1. Describe the transformations, graph, give the domain and range. Okay, now if there's a number inside the parentheses, what I've been stressing with you guys all year, factor out that 3 so that you get the correct transformations. So that 3 underneath, that is a horizontal compression by the reciprocal of that, 1/3. What I like to do, I like to find the reciprocal of that number. If that number's less than 1, I know it's going to be a compression. All right, now that -2, -2, that means right 2, opposite of what it appears to be. So, remember the parent function that we had graphed. You don't have to put it in, but you might want to put it in and then maybe erase it. Take that point 0, 0 that you had, shift it right 2. Now a horizontal compression by 1/3. That means that I go up 1, but over only 1/3. Try and put that in as best you can. I go up 2, I went over 4, so that I only go over 4/3. That's a little bit more than 1. So that's an idea of what that looks like. Your domain and range. Domain. Your graph starts there, goes to the right. So x is greater than or equal to 2. You started on your y-axis at 0 and you went up. So y is greater than or equal to 0. Cube root now. This is again the parent function that we're going to be graphing. So our parent function. Again, pick numbers for x that you know you can cube root. The cube root of 0 is 0. The cube root of -1. 3 of the same thing that multiply to be -1. That's -1. The cube root of 1 is 1. Now to go with your next cube root, the next perfect cube is going to be 8 and -8. Because the cube root of -8, 3 of the same things that multiply to be -8, -2. And a +2. So this is what your cubed root graph looks like. Because I can cube root negative numbers and positive numbers. Your domain is all real numbers. Since you go forever up and down, you get all real numbers out of it. So the difference in these is if you see a cube root, your domain and your range is always going to be all real numbers. If it's a square root, you're going to have restrictions. Okay, describe the transformations, graph the domain and range. Same thing that we've been doing. Underneath the radical, that +2, that's going to shift to left 2. -1, that's down 1. That negative, that's like a -1, so that's being multiplied to the whole function or the whole parent function. So that is going to be across the x-axis. So left 2. So normally you have the points. Let's talk about what the parent function looks like. Really the points I usually graph is 0, 0, -1, 1, 1, 1. And you have that kind of curve. It's not a straight line, it's a curve. Now you're going to take those 3 points essentially and graph them. So I start with 0, 0. I go left 2, down 1. And leave that point as is. Now this point here, goes left 2, down 1, but it gets flipped across the x-axis. So what happens is the curve ends up going the other way. That's what that curve looks like. Normally, if I didn't flip it across the x-axis, I'll put that in green, your curve would have looked like this. Your curve would have looked like that if you didn't do any flipping. If you flip, it goes across the other way. Using the description to write a square root function g of x, the parent function g of x is reflected across the x-axis. When you reflect something across the x-axis, you make the y's negative. So you multiply the y's by a negative. Compressed vertically, that's your y's, by a factor of 1/5. So I'm going to multiply the y's by 1/5 and translate it down 5 units. So I have this function f of x that I'm doing all of these things to. Okay, so again, let's look at this. Reflected across the x-axis, your y's get multiplied by a negative 1. Compressed vertically by a factor of 1/5. Y's times 1/5. Down 5, again, now that's y's minus 5. So nothing's happening inside the radical. So your new function, and you guys know I'm picky on this, I want g of x equals, because it's an equation. And weird things that math teachers are sometimes picky about. I like to see that an equation, when you're writing an equation, an equal sign, reflected across the x-axis, so that's a negative. Notice how I have it color-coded. Compressed vertically by a factor of 1/5. So I'm multiplying the y's by 1/5. Your parent function, so you know what you're graphing. And down 5, minus 5. Notice nothing was happening to the x's, so everything is outside the radical. All right, last one, graphing an inequality. This is just like graphing any old function. Just, that's going to be dashed. And then we have to figure out where to shade. Okay, so minus 3. So from 0, 0, what I do is I take that point and I go down 3. Now, vertical stretch by 2. This is what the 2 is doing. So normally I'd go up 1 over 1. Now I go up 1 over 2, up 2 over 1. It's a dashed line because I'm not equal to, just like you graph lines. Now, shading. Y is greater than that. Y is greater than that. That means I'm going to be shading everything above. Notice how I didn't cross that y-axis, because y's being negative are not part of your range. So that is what your function looks like. Make sure it's dashed and you have shading. There are your lesson questions for the day. Please make sure those are submitted on time.